This right here is known as the Sizzle and Slice Lab. Mr. Mark, my co-teacher over here, teaches AP1, invented this with a teacher back at his last school. The reason it's called Sizzle and Slice, we are going to sizzle here with a match in order for this to fall down and slice off at that razor blade right there. Now, this is an energy problem. Potential energy is going to turn into kinetic energy. But once it hits that spot right there, it's going to turn from an energy problem. I guess you could use energy to find the speed at the bottom, but we're actually going to try to figure out where it lands at the bottom of its swing here. Okay, so we need to have its change of potential energy. So let me go ahead and start measuring things. This one right here, and I'm reading from the top of it. This is 77.2. Go ahead and jump in there, get in there closer, get in there closer. So that's 77.2 to the top of it. Now why to the top? Because the top is going to hit the razor blade at the bottom, right? So then down here you can see that this is at 17. And then from the bottom, this is at 91. Okay, so now let's go to the board and let's record this, or let's figure out how this works. All right, so here's our situation. We have the ball and a string. We're going to cut it. It's going to swing down here. It's actually tied up here. We're going to sizzle this one with fire and a match. It's going to come down, hit the razor blade, and go off as a projectile. Now, if you didn't already know this, you have to figure out what the different situations are. This right here is conservation of energy, potential energy to kinetic energy. And we're going to use the change of potential energy. Okay, sorry, that's supposed to be the 17. Badly drawn. Sorry, let me get that just better drawn. So this is the 77, that's the table, okay? All right, so this is conservation of energy, and this is projectile motion. Let's do our calculations. So to find the velocity here, we know that our potential energy, our change of potential energy is going to turn into kinetic energy. The m's are going to cancel, both sides, and so our velocity squared is going to equal 2g delta h. Our velocity then is going to equal the square root of 2g delta h, which gives us square root of 20 times our delta h. Our delta h is going to equal 77 minus 17, which is 60 centimeters, right? So that's going to be 0.6 meters. That gives us a velocity of square root of 20 times 0.6, 3.5. I'm not going to use anything more precise than that because, well, it's not going to be that exact. So our x velocity, because it's going horizontal at that point, is 3.5 meters. Now let's go to do projectile motion. At this point, we have our x velocity being 3.5 meters, and our y velocity equal to 0, because horizontal is not vertical. Well, let's find our time to the ground. In the y direction, we will have delta y equals v initial times the time plus 1/2 at squared. Let's put in our numbers. There you go. So our distance, our complete distance to the ground is going to be 91 plus 17, 108. So 1.08 meters. Negative because it's going down. Why are there parentheses there? I don't know. This is going to be 0. And then we're going to have 1/2 times negative 10 times t squared. So that's going to be negative 1.08 divided by negative 5 equals t squared. Or t equals the square root. 1.08 divided by 5, which gives me a time of 0.46 seconds. Well, now let's find out how far it goes. Using in the x direction, there's no acceleration, so speed equals distance divided by time. Or our distance, which is actually the x distance, will be our velocity in the x direction times the time, or 3.5 meters times 0.46 seconds. And this ends up being 1.6 meters, which I will tell you that is farther than I expected it would go. So let's go over here, turn over here, and let's set up 1.6 meters. This is as close as I could get to below the object. It's actually a little bit far away. So somewhere about there. So 1.6 meters is way out there, which is farther than I thought it would go. So you're going to record up here, and we're going to record down there with slow-mo and see how we do.
Do you want me to like try to zip and?
I think you're just going to have to get that. Try to zip if you can.
All right.
But why don't you just mostly get this, okay? So again, I'm going to burn this rope up here. Hopefully it hits there. If not, this is going to be a real bust, won't it? Here we go. Oh, I hit it right on, didn't I? Did you get it?
Yes.
All right. Oh, I hit it right on, didn't I? Did you get it?
Yes.